ocean of molten rock. Constant volcanic eruptions, driven by tidal forces and internal heat, continually reshape the landscape, turning it into an ever-changing inferno. Beneath this molten crust, scientists theorize a thick layer of carbon compressed into solid diamond, a fascinating scenario earning this planet its famous nickname, the Diamond Planet. Yet, despite the allure of diamond-rich layers, conditions here are violently inhospitable. The atmosphere, if present, would likely consist of dense, toxic gases, including vaporized metals and silicates, completely hostile to life as we understand it. These brutal conditions have captivated researchers eager to understand planetary processes under extreme environments. What makes this celestial body even more fascinating is how it defies existing theories of planet formation. With a mass roughly 8 times that of Earth, astronomers puzzle over how such a massive rocky planet formed and migrated so close to its star. Studying this phenomenon may fundamentally alter current models of planetary evolution and orbital dynamics. Advanced telescopes such as NASA's James Webb Space Telescope aim to uncover more details about the exoplanet's atmospheric composition, volcanic activity, and potential chemical processes. New insights could emerge from observations, possibly revealing unknown geological phenomena, or unprecedented chemical reactions taking place under these extreme conditions. Astronomers speculate about intriguing possibilities such as immense metallic storms or exotic auroras caused by strong magnetic fields interacting with stellar radiation. Others consider the existence of seismic activities or tectonic shifts so powerful that the planetary surface could dramatically change within days. If confirmed, these phenomena would represent entirely new planetary processes unknown within our solar system. Additionally, researchers ponder whether the gravitational interactions with nearby planets could influence internal planetary dynamics, potentially creating rhythmic volcanic cycles or geochemical pulses. Understanding such intricate gravitational resonances could significantly advance our knowledge of planetary systems. Ultimately, this extraordinary exoplanet serves as a natural laboratory, allowing scientists to explore the extremes of planetary physics and chemistry. Each new discovery reveals yet another unexpected mystery, reminding humanity of the infinite complexity and wonder inherent within the cosmos. As scientific exploration of this exotic planet advances, astronomers consider increasingly daring theories. Could the intense gravitational interactions with its star create powerful internal magnetic fields, generating spectacular electromagnetic phenomena such as metal-rich auroras? If so, telescopes might someday detect these dazzling displays, fundamentally reshaping our understanding of planetary magnetism. Moreover, some researchers theorize potential for rapid orbital decay, where tidal interactions gradually pull the planet even closer to its star. Observing such a dramatic event would provide unprecedented insight into planetary destruction and offer direct evidence of the dynamic nature of planetary orbits. Another exciting possibility involves transient geological phenomena driven by the extreme internal pressure and heat. Scientists speculate that beneath the molten surface, conditions may periodically produce exotic mineral formations or even temporary states of plasma-like materials. Capturing observational signatures of these phenomena could significantly expand our geological knowledge. Intriguingly, astronomers also imagine how this carbon-rich planet's extreme conditions might foster unique chemical reactions. Could the intense stellar radiation and high temperatures drive previously unknown photochemical or nuclear processes, generating new molecules or isotopes? Detecting such compounds would challenge existing chemical theories and inspire entirely new fields of astrochemical research. Future technologies, including specialized instruments and powerful observatories, might soon allow scientists to detect subtle variations in the planet's emitted radiation, providing clues about hidden internal processes. Detailed studies of atmospheric composition, surface volcanism, and magnetic interactions with the star could reveal unexpected cycles or rhythms, offering insights into planetary stability under extreme conditions. Additionally, whether the extreme geological activity might occasionally propel mineral-rich debris or diamond particles into orbit, forming transient rings or clouds around the star. Capturing visual evidence of such events would dramatically illustrate how planets influence their stellar environments. Each new theory and discovery about this distant world not only expands our scientific horizons but also deepens humanity's philosophical reflections about the nature of the universe itself. By challenging existing models and inviting speculation about previously unimaginable processes, this extraordinary exoplanet continues to ignite scientific curiosity, driving humanity to push the boundaries of exploration ever further into the cosmic unknown. As astronomers continue probing the mysteries of this extraordinary exoplanet, speculation emerges regarding hidden, deeper phenomena beneath its volcanic surface. Could enormous subsurface currents or tides of molten rock circulate within the planet's interior, driven by gravitational friction and internal heating? Detecting these hidden magma currents could revolutionize our understanding of planetary geology under extreme gravitational stress. Furthermore, scientists theorize the existence of unusual seismic activity, perhaps massive tectonic movements or planet-wide tremors, caused by tidal forces. If observable from Earth, these seismic events could offer invaluable insights into the structural integrity and geological processes of rocky planets under intense gravitational conditions. Another captivating possibility is the formation of entirely new, transient minerals created by extreme pressures and temperatures beneath the planet's crust. These minerals might appear and vanish rapidly, cycling in response to volcanic eruptions and internal pressures. Observations capturing these fleeting geological events could significantly enhance our knowledge of mineral formation processes under extraordinary planetary environments. Researchers also consider the potential for dynamic atmospheric phenomena. Could vaporized metals form turbulent storms or metallic rain, periodically reshaping the planetary surface? Detecting atmospheric events composed of vaporized silicates, iron, or other exotic materials would profoundly expand our understanding of planetary weather systems. Moreover, the planet's proximity to its star raises questions about complex magnetic interactions. Powerful stellar winds interacting with the planet's magnetic generate astonishing auroral displays or electromagnetic storms detectable by advanced telescopes. Understanding these interactions could provide crucial data for refining theories about planetary magnetic fields and stellar influences. This fascinating world also inspires questions about how planets evolve under extreme orbital migrations. If the planet once orbited farther from its star, how did it migrate inward, and what violent interactions forced this change? Analyzing such orbital history could yield valuable insights into planetary formation and the stability of planetary systems. In the future, groundbreaking observational techniques, perhaps even remote seismic measurements or highly detailed spectroscopic analysis, could allow astronomers to study surface movements or atmospheric changes directly. Such advances would offer an unprecedented glimpse into the real-time dynamics of distant worlds, transforming exoplanetary research. Ultimately, the continued exploration of this intriguing exoplanet emphasizes humanity's insatiable curiosity about cosmic extremes. Each new discovery pushes us to reimagine what planets can be, driving scientific and reinforcing the awe-inspiring complexity and creativity of the universe. Further exploration into this captivating exoplanet invites us to consider scenarios previously unexplored by planetary science. For example, scientists have begun theorizing about the intriguing possibility that gravitational resonances between the planet and other bodies within the 55 Cancri system could trigger episodic upheavals. These hypothetical gravitational tides might periodically fracture the crystalline diamond layers beneath the molten crust, releasing vast quantities of carbon-rich materials and fueling massive volcanic eruptions, visible even from Earth-based telescopes. Moreover, researchers speculate about whether this exotic planet might exhibit magnetic reversals far more rapid and chaotic than those recorded on Earth. Such extreme fluctuations could result from the planet's rapid rotation, intense tidal stresses, and highly conductive molten interior. Observing these shifts in magnetic orientation remotely would offer unprecedented evidence of how planetary magnetic fields behave under extreme conditions, potentially transforming astrophysical theories. Astronomers also envision scenarios where the planet's immense heat and gravitational forces might occasionally generate enormous atmospheric eruptions, storms composed of vaporized metals or rapidly condensing diamond dust. These events could briefly alter the planet's reflective properties or spectral signature, providing rare glimpses into transient planetary processes. Capturing these phenomena could yield extraordinary insights into the exotic chemistry and atmospheric dynamics occurring at the fringes of planetary science. The planet's volatile surface environment might also result in cyclical chemical processes, where exposure to intense stellar radiation continuously drives transformations in surface chemistry. Complex cycles of melting, crystallization, and sublimation could repeatedly alter the surface composition, forming compounds and crystals previously unseen in nature. Studying these chemical cycles might significantly expand our understanding of mineral stability under cosmic extremes. Another captivating whether gravitational interactions with its host star could result in subtle shifts in stellar behavior itself. Could this planet's relentless gravitational tug influence stellar activity, magnetic cycles, or flare production? If such a planetary-stellar connection were confirmed, it would fundamentally reshape how scientists perceive the relationships between stars and their orbiting worlds. The exoplanet's extreme nature also inspires ideas about future exploration technologies. Advanced observational platforms, employing high-resolution spectroscopy and gravitational wave detectors, may soon capture precise data about surface movements, internal seismic activity, or even atmospheric chemistry. Such data would provide groundbreaking insights into planetary behaviors in exchange. Finally, this compelling exoplanet symbolizes humanity's drive to push beyond conventional limits, constantly challenging what we believe possible. Each new revelation encourages astronomers and scientists alike to venture further into the unknown, forever expanding our view of a universe filled with endless diversity, beauty, and mystery. As our exploration deepens into the mysteries surrounding this exceptional exoplanet, new speculative ideas continue to captivate researchers. Some astronomers propose the existence of colossal underground caverns or voids deep beneath its molten surface, spaces carved by enormous pressure fluctuations, gravitational shifts, or tidal forces. Within these vast subterranean chambers, unique mineral deposits or exotic crystalline formations could exist, isolated from the turmoil raging on the surface. Such hidden realms would profoundly expand our understanding of geological processes under unprecedented planetary conditions. Equally intriguing is the potential discovery of periodic shifts in the planet's magnetic field intensity, generated by interactions between its dynamic interior and fierce gravitational forces. Could these magnetic fluctuations trigger remarkable electromagnetic events, observable as pulses of radiation or magnetic storms visible from Earth-based instruments? Detecting such phenomena would offer incredible opportunities for astrophysicists to study magnetic dynamics under extremes never previously encountered. Scientists are also fascinated by the possibility of this planet periodically ejecting significant portions of its atmosphere or surface material into space due to explosive volcanic activity or tidal disruptions. Such dramatic events could create temporary clouds of vaporized rock and diamond particles orbiting the star, altering the system's brightness or spectral signals. Capturing observational evidence of these cosmic spectacles would provide extraordinary proof of how planetary systems evolve and influence their stellar surroundings. Additionally, speculation grows about whether extreme chemical reactions driven by intense stellar radiation and gravitational forces could produce exotic, transient compounds with novel chemical bonds, or even new forms of carbon-based matter. Detection of such reactions would revolutionize astrochemistry and perhaps open entirely new possibilities in material science. Even gravitational theories might evolve from studying the dynamics of this peculiar world. Could the planet's orbit exhibit subtle yet measurable gravitational anomalies, minute irregularities pointing to previously unknown physical interactions between massive planets and their stars? Analyzing these orbital variations could refine gravitational models and deepen our fundamental understanding of gravity's role in shaping planetary systems. Furthermore, this distant planet's extreme nature raises broader scientific curiosity regarding planetary classification itself. Could it represent a previously unrecognized planetary type, one defined by extreme geological processes, rapid orbital dynamics, and unconventional chemistry? If so, identifying and understanding this new class of celestial bodies would significantly reshape planetary science, broadening our cosmic perspective. Each revelation about this extraordinary exoplanet highlights how exploration of extreme worlds continuously expands scientific imagination. In studying such enigmatic places, humanity comes face to face with questions that challenge our assumptions and stimulate revolutionary discoveries, fueling both scientific progress and a deeper appreciation of the universe's boundless diversity. Further into the mystery of this captivating exoplanet, astronomers imagine even more profound scenarios unfolding beneath its fiery facade. For instance, could the continuous, intense stellar radiation trigger electromagnetic phenomena at the planet's surface, potentially generating localized magnetic anomalies or plasma-based phenomena? Detecting these exotic surface activities could open up entirely new areas of astrophysical research and lead scientists toward unexplored physics governing stellar planetary interactions. Additionally, the planet's extreme gravitational forces might produce remarkable geological activity unlike anything encountered within our solar system. Researchers speculate about the existence of evolving volcanic mountain ranges or constantly shifting continental plates composed of solidified carbon structures. Active geology, changing visibly gradually within short periods, would provide an unprecedented opportunity to study planetary tectonics operating under conditions dramatically different from Earth. There is also speculation about hypothetical phenomena known as diamond rain occurring within the planet's atmosphere, where vaporized carbon compounds might condense into tiny diamond particles, gradually falling back onto the molten surface. Observational signatures of these spectacular events could dramatically enhance our understanding of exotic weather systems and offer tangible evidence of how chemistry operates in extraordinarily harsh environments. The planet's gravitational influence on its host star might even extend further, possibly inducing subtle stellar pulsations or magnetic fluctuations. Observations of such star-planet interactions would yield remarkable insights into the mutual gravitational effects between massive terrestrial worlds and their parent stars, reshaping how we interpret planetary evolution in extreme environments. Researchers also theorize about the existence of transient atmospheric windows, brief periods when volcanic activity subsides enough to allow clearer observations into the deeper layers of its atmosphere or surface. Moments with precise telescopic observations could provide invaluable opportunities to gather data about atmospheric compositions or volcanic activity previously obscured by constant geological turmoil. Moreover, some scientists envision that the planet's extreme gravitational conditions might occasionally produce gravitational waves or seismic tremors detectable by advanced observational instruments from Earth. Such groundbreaking detections would offer astronomers the unprecedented ability to study planetary geology directly through gravitational wave astronomy, pioneering a remarkable new frontier of cosmic observation. Exploring worlds like this fiery super-Earth continually pushes human knowledge forward, inspiring innovation in astronomy, astrophysics, geology, and even philosophical reflection on our cosmic place. Each discovery encourages humanity to look further, to question deeper, and to appreciate more fully the boundless mysteries still waiting exploration among the stars. Scientists exploring the extraordinary nature of this distant super-Earth, now also ponder another fascinating possibility: the planet's capacity for exotic seismic phenomena. Could powerful tidal forces trigger global planet quakes, causing seismic vibrations capable of reshaping the planet's molten landscape overnight? If such seismic events occur regularly, they might influence volcanic eruption patterns, atmospheric dynamics, or even surface chemistry in ways never before observed. Equally intriguing is the potential existence of exotic interactions deep within its molten interior. Phenomena such as spontaneous formation of novel carbon-based alloys, superconductive, or even complex compounds born from the interplay between extreme pressure and heat. Discovering these hidden geochemical processes would significantly advance our understanding of how extreme planetary can produce unexpected chemical states of matter. Scientists are also considering how the planet's extreme gravitational relationship with its host star might influence stellar flares or magnetic storms, potentially causing episodic bursts of stellar radiation. Detecting these interactions would demonstrate that planets, even rocky super-Earths, might significantly affect the behavior of their host stars, an exciting possibility previously reserved mostly for giant planets like Jupiter. Furthermore, astronomers speculate that subtle gravitational waves, ripples in spacetime caused by intense planetary star interactions, could emanate periodically from this system. Advanced gravitational wave observatories of the future might someday detect faint signals from these distant tidal interactions, providing groundbreaking evidence of planet-star dynamics on a cosmic scale. Additionally, the extreme temperature gradients between the planet's eternally hot daylight side and permanently shadowed hemisphere could create powerful global convection currents in its atmosphere, driving massive, hurricane-like storms of molten vaporized minerals. Observing these spectacular planetary storms would offer unprecedented insight into atmospheric dynamics under severe thermal stress. Even speculative discussions of hidden planetary, not of water or molten metals, beneath its blistering crust continue to intrigue planetary scientists. Such bizarre oceans might host unexpected geochemical reactions, possibly generating transient mineral formations or even unusual chemical cycles that continuously alter the planet's internal structure and surface chemistry. Ultimately, each fresh observation about this captivating planet further reveals the immense complexity and creativity of nature, continually redefining the boundaries of planetary science and exploration. As telescopes and technology advance, astronomers remain confident that this distant and mysterious world will continue to yield remarkable discoveries, deepening our curiosity about the limitless diversity of planetary conditions throughout the universe. As astronomers continue unraveling the fascinating mysteries surrounding this enigmatic celestial, possibility emerges that beneath its scorching surface might lie hidden gravitational anomalies capable of influencing planetary structure at microscopic scales. These subtle anomalies could trigger localized pulses of extreme pressure, potentially creating transient pockets of exotic crystalline structures, briefly formed, then shattered by volatile upheavals. If such transient geological formations exist, their discovery could dramatically enhance our understanding of planetary interiors under unprecedented stress conditions. Researchers also consider sudden bursts of intense volcanic activity might periodically reshape the planet's atmosphere, ejecting enormous clouds of vaporized metals and minerals into orbit. Such explosive eruptions could temporarily envelop the planet in reflective metallic clouds visible from Earth, creating spectacular changes in brightness and spectral signatures. Observing these dramatic planetary scale events would provide insight into extreme volcanospheric evolution on worlds experiencing relentless stellar radiation. Even more provocative are theories suggesting that the planet's extreme gravitational environment might drive exotic quantum phenomena deep beneath the molten surface. Could the immense pressures and heat generate fleeting states of matter, such as metallic carbon alloys or superconducting crystals, that briefly emerge before disintegrating into molten chaos? If detected, these short-lived phenomena could prompt scientists to reconsider fundamental theories of stability and diversity of matter in the cosmos. Astronomers are also intrigued by the possibility that gravitational interactions within the planet's orbit might create complex resonances or harmonic patterns involving neighboring planetary bodies. Such subtle gravitational interplay could influence internal geological processes, perhaps triggering rhythmic eruptions, seismic activity, or atmospheric fluctuations on predictable intervals. Understanding these subtle resonances might open entirely new avenues in planetary dynamics research, offering deeper insights into how planetary systems sustain stability. Fascinating question about the planet's magnetism. Could intense internal friction and tidal stresses generate electromagnetic bursts detectable from Earth? Observing such phenomena might not only revolutionize our understanding of planetary magnetism, but also help scientists identify new ways to search for and characterize extreme planet star systems across. In some scientists, their technologies might someday enable direct imaging or remote analysis of transient geological events, such as sudden resurfacing of solid diamond layers, temporary magma lakes, or storms of metallic vapors, transforming our theoretical understanding into observable reality. Developing these advanced observational capabilities would profoundly advance astronomy, expanding humanity's ability to witness planetary phenomena in unprecedented detail. Ultimately, this distant, enigmatic planet symbolizes both the infinite complexity and boundless potential of the universe. Each Each unanswered question and surprising discovery fuels human curiosity, inspiring scientists to explore further, question deeper, and imagine wider, pushing the limits of our cosmic understanding and revealing that the universe is vastly richer and more astonishingly diverse than we ever dreamed possible. Continuing exploration of this extraordinary exoplanet raises provocative questions about how planets behave in extreme stellar proximity. Astronomers contemplate whether gravitational interactions might induce unusual planetary pulsations, rhythmic expansions or contractions of the planet's interior, driven by tidal forces from its star. Such pulsations could periodically alter the planet's density distribution, potentially affecting volcanic activity, seismic events, or even the structure of its hypothesized diamond core. Moreover, the extreme conditions of this planet inspire ideas about previously unseen atmospheric chemistry. Could ongoing volcanic eruptions and stellar radiation combine to form dynamic cycles of chemical reactions, creating transient atmospheres composed of exotic gases or particles never before documented? Detecting such phenomena could transform our understanding of atmospheric chemistry under severe stress. Intriguing also is the possibility that intense surface conditions might produce exotic forms of lightning, generated by friction and collisions within dense metallic clouds. Massive electrical storms spanning continents of molten rock, illuminating the perpetual twilight regions between blazing daylight and absolute darkness. Capturing evidence of these spectacular electric phenomena would not only amaze scientists but also provide crucial insights into electrical processes on extreme worlds. Another compelling scenario involves planetary-scale convection currents, by extreme temperature differences between the illuminated and dark hemispheres. These currents might continuously transport heat, minerals, and carbon-rich matter around the planet, creating cycles of geological renewal and destruction. Evidence of such planetary-scale circulation could revolutionize geophysical models and enhance our understanding of internal planetary dynamics. Scientists also consider whether extreme orbital conditions could lead to unusual patterns in surface gravity, possibly producing areas of shifting gravitational intensity across the planet's landscape. These gravitational anomalies might periodically trigger massive collapses or eruptions, creating a uniquely chaotic and unpredictable surface environment. Studying such gravitationally driven phenomena would deepen comprehension of planetary surface behavior under extreme conditions. Additionally, some researchers ponder the possibility of observing reflections of stellar radiation from transient atmospheric structures or layers of crystallized carbon temporarily exposed by volcanic activity. Detecting spectral variations indicating brief windows into otherwise hidden planetary layers would provide astronomers with valuable information about its geological composition and evolution. Ultimately, each new question and discovery surrounding this fascinating planet underscores humanity's endless quest for cosmic understanding. By exploring worlds of unimaginable extremes, astronomers continually expand the boundaries of our knowledge, inspiring generations to dream of discoveries yet to be made and phenomena yet to be imagined. Astronomers continue to theorize about hidden mysteries deeper beneath this planet's fiery exterior, and possibilities even more exotic and captivating. Could powerful gravitational resonances within its planetary system occasionally trigger immense internal pressure waves, propagating through the planet's molten layers, causing dramatic surface upheavals? Such phenomena, if detected, might unveil a cosmic rhythm underlying planetary systems, enhancing our understanding of celestial dynamics. Furthermore, the extreme pressures at the planet's core might foster states of matter entirely unknown to modern physics, perhaps transient phases of matter where diamond, graphite, or metallic carbon exist simultaneously in fleeting equilibrium. Discovering these transient materials could offer breakthroughs in materials science, influencing our understanding's versatility and extreme conditions. Astronomers are also fascinated by the potential for observing transient events such as immense volcanic explosions powerful enough to reflectivity or even temporarily obscure its visibility. Witnessing these explosive events, telescopes would provide rare and invaluable data, showcasing planetary processes on a scale previously impossible to study. Additionally, the planet's surface might periodically experience massive fractures, through which molten interior materials erupt with unprecedented force. Such volcanic episodes could temporarily expose inner planetary